Hello, everybody. We want to welcome our friends from all parts of the world. Thanks for tuning into the Dupont Water Academy channel. These wave webinars have been something else. We are getting great feedback from you along the way. And the responsible for that is our very own scientist and inventor, the father of wave, Garth Parker Jr., and the subject matter experts that he brings along every time that I introduce to you in just a moment. So today, Garth and his guests will take you through a deep dive into Dupont's water application value engine, WAVE software, focusing on mixed bed ion change resins. We hope you enjoy this free webinar program and make the most of the engagement tools by downloading your certification of attendance, which, by the way, offers PDH credits, making questions, and always sharing your feedback with us. So let's take a look into these cool icons in your dashboard. You can access any of the engagement resources from the bottom of your screen by simply clicking on the colored icons, and you can resize and move them around as you wish to best fit your screen. So this is a deep dive. You may already have the program, but for those who are interested, you can find a link to download WAVE in the resource list, thanks to our webinar producer, Inga Arson. We would appreciate to hear from you, and the best way to raise your questions or comments is the purple Q&A box in the lower left corner. If your question is longer or would like to have a more personal response afterwards, you can do that with the blue Contact Us button. So don't forget to submit your questions throughout the presentation, because we have another expert here today, Mark Slack, that is exclusively dedicated to address your questions right away to the chat offline. Let's just remember that in the resource folders, you're going to find any relevant material to this presentation, and including the link to register for the WAVE series that started a while back and has been going throughout the year. And including in your dashboard as a featured link, you're going to see the registration available for the next WAVE session on December 15th to advance your skills on CCRO membranes. All right, now back to our topic. And our speaker today, Garth Parker Jr. is a research scientist in the Technical Service and Development Group of Dupont Water Solutions, based in Philadelphia, United States. He has worked for 32 years for Roman, Dow Chemical, and Dupont, primarily in applications development and modeling of water treatment technologies. He has been the technical leader of the WAVE development team since the project's inception. Garth has a PhD in chemical physics from the California Institute of Technology. And today, two of our Exchange senior engineers will be supporting Garth by bringing relevant questions from the audience to him. And they are Matt Roth, Technical Service Manager supporting members and Exchange product lines for DuPont Water Solutions in North America, and Donna Murphy, Senior Technical Service and Development for DuPont Water Solutions. Being her field of expertise, ion exchange in industrial water applications. So I'll leave you now with this amazing team, and I think Donna, you're going to get us started.
Yes, thank you, Laura. Thank you. So hi, everyone. I'm happy to be here with you today, along with my colleagues, to talk about mixed bed design using WAVE. Today, we're going to be talking about some design constraints or challenges that you may face in working through a mixed bed. Having a robust design for mixed beds are very important, since most commonly they're used as the last stage of defense when protecting your valuable equipment or processes. So fortunately, WAVE's going to alert you to some warnings that may arise when you're designing your mixed bed. Specifically like some hydraulic, if you're out of range for hydraulics or other recommended parameters. And Garth's going to demonstrate today how to improve the design and clear those warnings. Also, we're going to focus on the use of a degasifier in WAVE. We have to give special consideration to the proper setup for degasifiers when they're placed in front of mixed beds. And Garth, who's my go-to expert in CO2 chemistry, will walk us through the proper way to use WAVE using the degas functions. So let's get started. So our first example today is going to be a working mixed bed. And this is a case where we're not going to have any pre-treatment up front. The mixed bed's going to be treating well water with a TDS around 90 ppm. So Garth, you want to get us started?
Sure. So thank you, Donna. So for this first example, we're going to be looking at a working mixed bed. And you can get a working mixed bed actually out of the standard demineralization icon. So we'll drag and drop our demineralization icon, and then we'll go up to the feed water tab, and we will load, we have a water there, which is a fairly low TDS well. Water. It has a TDS of about 90 milligrams per liter. A lot of it will be bicarbonate and silica. So we will copy this to the feed water and then move on to doing the design. Normally we would design for one train online and one train in regeneration or standby, especially for a working mixed bed. One of the features of WAVE is you can design mixed beds based on the space velocity, which for a working mixed bed will keep a little on the low side. So we'll keep it at about 20 BVs an hour.
Thanks, Garth. And I just wanted to comment on the spatial velocity here, that typically for working mixed beds, it's between 15 and 30 BVs per hour. But Matt, do you want to comment on for applications maybe like UPW or nuclear?
Yeah, so in most power applications, Donna, thanks for the question. Most power applications, we would usually, for condensate polishers, we would look at linear velocity as the guiding max flow range, and we would usually be looking at a linear velocity of around 50 GPM per square foot. And maybe Garth, you know that offhand in metric. But then for UPW, you'd be looking at a lower range, more like 25 GPM per square foot as a max. So
yeah. So in designing things with lower TDS, much lower TDS, your BVs per hour would be much faster. So would be much higher, I should say.
Yep.
So keep that in mind.
Okay, so some of our later examples, I think, will show going up to higher flow rates. Okay, so we have specified that we'll be running at 20 BVs an hour. Now we'll just step through like most any other wave design. For the mixed bed, it's all the way down here at the bottom of the resin arrangement. You pick a mixed bed at automatic for the cation. It will automatically pick it for the anion.
Just one question that came in that would be relevant as we're going is, what is a BV? Donna, if you just want to give a quick explanation.
Oh, sure. A bed volume is is a reference to the volume of resin that's in your vessel. So, however cubic meters are in the vessel, that is the bed volume.
Right. So a specific velocity of 20 BVs an hour would be, if you have a 1 cubic meter vessel of resin, you would be flowing water at 20 cubic meters an hour. So it's volume of water divided by volume of resin.
And if you weren't comfortable with BVs an hour, you can switch that in WAVE. It'll go in other units as well. So
yeah. Okay. So we'll pick a mixed bed, and you can verify you have a mixed bed. You get your nice little diagram here off to the side, which will show you that you have a mixture of two resins. Next, stepping through the usual WAVE screens, you get your resin selection. One of the good things about WAVE is anyone who's worked with mixed beds knows that you have to have certain combinations of resins have the correct particle size and density to work. And you can't necessarily pair every cation resin with every anion resin. So WAVE will take care of that for you by, as you select a cation resin, the list of anion resins will change, and vice versa. If I select a cation or anion resin, it will modify the list of cation resins that are compatible with it. So it will go back and forth as you make selections to make sure that you have a compatible list. For this particular mixed bed, we're going to choose, I believe, 1200 hydrogen and 4200 hydroxide as sort of the standard resin combination we recommend for mixed beds. Moving on, we're going to just select as our regenerants hydrochloric acid and sodium hydroxide. Just take the defaults everywhere, and we'll take the defaults everywhere for the program. And having accepted all the defaults, we'll now click on Summary Report and generate the mixed bed design. So a couple of things to quickly check. We specified a feed flow of 100 cubic meters an hour. Therefore, and we specified that we wanted a 20 BV an hour flow rate, which means we should have a resin volume of 5 cubic meters. And we got 4.98 because of rounding. So that is, in fact, the expected resin volume. Looking at the resin volume in the reference form for the two components, you can see that we have twice as much anion resin as cation resin. That is the limit that WAVE will accept for a mixed bed. So you'll have either essentially 66% of anion resin up to 66% cation resin. So that's the range that we recommend for most mixed beds. The rest of the report is fairly standard. You can confirm as we get down here that we hit our 20 BVs an hour target. Pressure drop looks acceptable. And then water quality met the targets.
And
so now we
Garth,
look.
Garth, while you're talking about water quality, can we just briefly touch on the feed water quality? Donna, I think you had this in mind as something that would be good to share, but could we comment on what a typical max TDS might be for a working mixed bed application? That's come in a couple times actually through Q&A.
Sure, no problem. So typically for a working mixed bed to be economical, the feed water is usually around 100 ppm or less. And you can see, I guess, here, how many hours did this one give us, Garth?
Okay, so if we scroll back up to the top of the report, we'll see that in this design, we had a roughly a 9-hour, 15-minute or so run length with a 90 ppm TDS. So, and the regeneration time's 4.5 hours. So,
right. So we're going to see if we can improve on that.
Yep.
Through this design, yeah. Thanks.
But yeah, so that's getting to be a pretty short run length, given the length, how much time it takes to regenerate it. So, and that was at 90. Okay. If we just scroll back down to the bottom, you'll see we had one warning, which is the regeneration velocity was a little low. The calculated value was 1.9, and the limit that we recommend is 2. This is actually a very common warning to be seen in mixed bed designs, and that occurs because, as we discussed earlier, we have a bed that's predominantly anion resin, but the regeneration conditions are set based on the cation resin. And so when you get a 1-part cation to 2-part anion, you can get that warning message. That's actually very easy to eliminate. We go back to our design screen and we go up to this advanced regeneration page. And there are 2 numbers here that are controlling the regeneration. This 3.5 here is the specific velocity, or 3.5 BVs an hour, that we're using for the cation resin. And then the linear velocity of the anion of the sodium hydroxide is set to be just slightly above the linear velocity of the hydrochloric acid, based on this ratio of 110%. So these 2 numbers working together set the flow rate for the sodium hydroxide. So we were just a little low. So we want to just increase this just a little. So we'll say we make that 3.7. Yes.
While we're on this page, that ratio that is there, the 110, if an OEM had their own methodology for that, is that something they could change here as well?
Yes, that is a number in a white box, so it's user editable. we usually keep the, as a default setting, we usually set the downward flow of caustic just slightly higher than the upward flow of hydrochloric acid, just to make sure everything stays well compacted and you don't start fluidizing anything. Okay, having raised this from 3.5 to 3.7, if we rerun the design, that's had essentially no change on the run length. Because we sped up the regeneration a little, we actually shortened the the regeneration time. And if we scroll down to the bottom, we see that we got rid of the warning, as expected, by slightly increasing the flow rate of the regenerant. Okay, so that's how you can solve the most common warning that would show up in a design. If you have a different water, so you have a more even match between anion and cation load and capacity of the two resins, so you're maybe a 50-50 mixed bed, you typically wouldn't see that warning. Okay, so one of the things we were looking at is we have a fairly short run length. We're only getting about a little over 9 hours of expected run length. And one of those, as we mentioned before, is we have the feed water in this design has a lot of CO2 and bicarbonate, as well as silica. And in waters with lots of CO2 and bicarbonate, you might ask, well, can I get rid of some of the CO2 with a degasifier and improve performance? And so that's easy enough to do in WAVE. We would go back to our design screen, and we would pick up this Add Chemical Degas button up here on the top, and we get this handy little window. One of the nice things about this window, if you are looking at the first icon in the treatment train, not only do you have the options of what you can do here on the top, you will get a little table here where you can see the impact of those changes on your water quality immediately. However, once you have multiple technologies in a row, you don't necessarily know what the water is, so you don't get this table for the second, third icon in the train, but you do get it for the first. So we will now pick our degasifier. See, we now have the label of what happens after you degas the water. And in many cases, if you're used to using a demineralizer, you might specify, okay, I know what my CO2 concentration will be, and I'll say, okay, I can get 10 milligrams per liter. And you get this really unusual result. It says that your pH is going to be 9.34, which doesn't make a lot of sense if you're used to normal demineralizer degasifiers. And this gets into the chemistry of degasification. When you specify a CO2 concentration, in this case 10 ppm, you're specifying the total amount of CO2, bicarbonate, and carbonate in the water. If you look at our starting water, we have a lot of CO2, but we also had a lot of bicarbonate, and this bicarbonate is being used to help charge balance the water. If I take out too much CO2, if I try to take out all of this CO2, I still have, most of this bicarbonate here for charge balancing. But if I take out more CO2 than that, I can't charge balance anymore, and the pH will start climbing fairly rapidly. The other way of thinking is you're taking out a lot of an acid, and so the pH will go up as you take out the acid. So this can sort of be seen if you just sort of, play with this number here. If we set it at 20, we took out a little CO2, barely touched the bicarbonate, and the pH is now 6.97. If we put this down to a really low CO2 concentration, the pH is going all the way up to 10. And if you wanted to see what happens if you pick the number higher than your feed, if I put in like 30 ppm, we actually added CO2 to the system. Right, we're keeping the bicarbonate the same. We've now added CO2, and we pushed the pH down. So you need to be very careful if you're doing a degasification in front of the mix bed, that you don't pick a number here that's unrealistically low. So there's a couple of ways to prevent that. One of which is being careful on where you set this number, and you can look at the pH and stop when you get to a pH that doesn't make sense. Alternatively, what I often do is I will use this middle button, where essentially I equilibrate the entire system with CO2 in the air. So if you're using an atmospheric degasifier, the current CO2 level in the atmosphere is about 410 microatmospheres or ppm by volume. And this would be the absolute best you could ever get with a degasifier running an atmospheric degasifier. So that would show you could bring the pH up to about 7.6.
And Garth, just in case people are wondering, that's a number that you would find published on some service online, right? Or that's a changing number.
That number changes seasonally by a couple of ppm, and as we burn fossil fuels, it's drifting up over time. But for the purposes of this calculation, you don't have to get really exact on it. 410 is a good ballpark number for right now. The reality is any degasifier is not 100% efficient at removing CO2. It's going to leave some behind. So I might typically leave this number at about 1,000. So this allows you to essentially equilibrate the CO2 in the water with CO2 left in the air. But you can see what happens if you come over here. You could change the temperature, because all these equilibrium expressions are functions of temperature. So if I go down to the minimum temperature or the maximum temperature, you can see the CO2 level here will change as I play with the temperature. Now you could ask, the reason I can't do, a lot of degasification is I have a lot of bicarbonate in the water. It's being used for charge balance. So you could ask, well, what happens if I add acid? Well, you could come up here to our previous button, click on it, and I'm going to add a trace amount of hydrochloric acid. And if I add acid, say to a pH of 5, I drop the pH. I convert almost all of that bicarbonate into CO2 because I lowered the pH, and I now have all that chloride adding to my TDS. As I degasify the system, I actually get rid of a lot of it to the CO2, so now I have a lot less CO2 and bicarbonate left behind. And so you can now look at the interaction of, does it pay to add a little acid with a degasifier to reduce the total ionic load? So here we've added some chloride as HCl to lower the pH, then degasified. So we've essentially converted, changed the feed water chemistry. So if we go back and rerun the design, we bought ourselves about extra 45 minutes of run length by adding a little HCl and a degasifier. And you can go back and forth between the degasifier page and here if you want to try to find the sweet spot where you would get, at your design temperature, the best performance.
Right. And I just wanted to stress the importance of what you just demonstrated, Garth, because if we incorrectly, use this function, we're affecting our feed water, and that's going to impact our design and the performance. So, like Garth said, when you're not using the degas in between a 2-bed sac and SBA, where, all the alkalinity is basically converted to CO2 because of the low pH coming out of the cation. You really need to pay attention to your CO2 equilibrium, and using that option with the partial pressure is much better than locking in a certain value of what you think the degas is going to be, performing at. So you could run into trouble there. Yes. So.
Correct, Donna. And like I said, the best way to verify it is simply watch your pH. If your pH gets much above 7, you've over-degasified. Mm-hmm. And I don't know if you would
pick that up, right, Garth? If you don't have that degas screen open that shows you those values, and so that's a good thing to have. And yes, keep an eye on the pH, like Garth said. Thank you.
Yes, Garth. we had one person that over degasified, and they had a pH of 10 here. They're wondering, how did they get a feed water pH of 10? And that's where we got into this whole discussion of the correct level of degasification. Okay, Donna, do you have any other questions about our working mix bed, or?
I think we had a question that came in from the audience about resin selection and why the 1200 and not the 1300. So our 1200 is about 8% DVB, and traditionally in mixed beds we had used the 1300 because it had a nice contrast in color between the anion, and the 1200 now is an improved version and is darker, so we can now use it. So our traditional Marathon C, which is now our Amberlight HPR 1200, can be used, is dark and can be used in a mixed bed, which it's nice if you already have a 2-bed Demon system where you're using that in the cation, the primary cation, and so you can just streamline and have one. But either one can be used. The 1300 or the 1200, but I just wanted to answer that question. And
sure.
Do we have any?
Something else that came in that might be good to show is, can you just show again how to find that degas option, and then maybe just distinguish how this one's a little bit different than if you're going through a standard Demon train? But
sure. Okay, so the degas, we go back to our demineralization screen where you would enter all your normal options, and you get your whole list of the different screens you go through over here. At the top here is the button called Add Chemicals and Degas. And so this is what gets you into the screen. If you want to see the reason why it's different than a standard demineralizer, you could actually lower this pH to about 3, which is what you would have coming off a normal cation part of a demineralizer. And then you have a very low pH. All the alkalinity's been converted to CO2. And if we just go back to here, I can set this to a very low number. And I have so much acid in there, even though I take out all the CO2, I haven't budged the pH. So that's why on a demineralizer where you're working with a very acidic stream, this isn't really critical what value you put here. But if you're working with a working mixed bed where your starting pH is near neutral, it is very critical to not over degasify, because you'll specify something that's just not reasonable, not possible.
But, okay. Garth, maybe just to distinguish, if you close this out, that button again was at the top of the screen, and if you were doing a standard demineralization projection, you would be prompted within this lower section as to whether or not you were wanting to add a degasifier.
Right. This button here, this button here always places the degasifier in front of the system. So it would be in front of. For a working demineralizer of a separate cation, anion, and separate vessels, you would actually have an option here underneath the diagram to add a degasifier tower after the cation, before the anion. So this button sticks it in front of everything, and as long as you have multiple vessels, you could do it right here. There'll be an option to turn on a degasifier, and you get the same sort of options for partial pressure or total CO2.
Okay.
Okay.
All right. So, are we ready to? Do you think we're ready to move to the next example?
I believe so.
All right.
So
okay.
we will go
so
start a new.
Yep. If you want to start a new case, Garth. And in this case, you and I had talked about running through an example of a mixed bed downstream of RO this time.
Right. So in this case, we're running actually the same feed water, but we're going to run it after an RO system. And I designed
And this is single pass, right?
This is a single pass RO system that I designed previously at 75% recovery. So we will put in a polisher. After the RO, you normally want to do polishing, so we would grab this IXMB icon from down here and drop that into place. The screens are essentially identical between the different ways of creating mixed beds. The primary difference will be the resins you can see, as well as the default limits. So that's the thing to keep in mind. Just because you're doing a mixed bed from a different icon, it's not like you have different screens to work with. It'll be the exact same screens, the exact same procedure to design it. You'll just have different limits. Okay, so continuing, Matt, I think we'll do our usual 1+1.
Yeah, and rather than length of operating cycles, can we start with a spatial velocity in the 50 BV an hour range?
Sure, so we'll go 50 BVs an hour. Down here, we're doing RO permeate polishing because we're coming after an RO system. Just going essentially the same as we did before. We're doing polish, so we will pick a mixed bed. Resin, we have a slightly different list of resins than we had before. So we'll pick the 4200.
We'll use an OH form.
Yes, I believe I used 4200 OH.
Yep.
Regeneration conditions. So, as I mentioned, a lot of the defaults are now we have, since we're polishing, we have lower default water quality specifications. So everything's specified, and we can go run our design. Okay, the RO report. So we are actually running this as a live connection between the RO and the polisher behind it. So we're actually going to do both designs every time we do the calculation. And if we make any changes to the feed conditions that would affect the RO, it will immediately propagate into the ion exchange downstream. So we now look at the ion exchange report. We had a feed flow rate of 100. We had a recovery of 75% in the RO system, so we have a feed of 75 for the ion exchange polisher. We asked for 50 BVs an hour, which is going to give us 1.5 cubic meters of resin. And once again, that was partitioned two anion resins to one cation resin. Because once again, the ionic load is very anion rich with weak acids. So we just confirm as we scroll down.
Check our spatial velocity.
We asked for 50, and after resin volumes got rounded, we got 49.96, close enough. We have a respectable pressure drop at the design temperature. And water quality meets the expected targets. Very nice conductivity.
Yeah.
And we look for the warnings. Okay, this time we have 2 warnings. We once again tripped this regeneration SV velocity issue, and we know how to fix that. So we'll go fix that our next pass to the design.
And you can see why we targeted that in the last example as a common warning. It's just something that tends to pop up every once in a while.
Yeah.
Go ahead, Garth.
And we also got a warning that if you looked at the total quantity of cation resin, its height or volume's a little on the low side. We'd like it to be about the equivalent of a 45 centimeter bed, and we're getting about 39 centimeters. So we're going to want to look to see what can we do to improve the height. So there are a couple things we'll do. I think the first one, since we know how to fix this ratio, we'll go fix it and just rerun it, because that'll prove we fixed it. And right, we fixed it. We only have the 1 warning. So now we can go back and look at what can we do to get the resin height higher. So there's a couple things we could do. Let's start by going to the final parameter screen here, and we can look at the volume of resin, the 2 resins we used, and the vessel diameter. One option, of course, is you could add more cation resin, which would give us a deeper bed, but we had specified the BVs per hour we wanted. So if we want to actually hold that BVs an hour, if I add cation resin, I should take away anion resin, and the system is limited by the amount of anion resin. So that doesn't really solve the problem. The other thing is that the wave optimization for bed diameter is going in 10 centimeter increments. So you could say, well, what happens if I reduce the bed diameter a little? So we could see if we put 120 for the vessel diameter, we'll see the design that Wave rejected as not being as good as the one it reported. So we get the quick calculation, we come back, we'll just jump straight to the warnings, and you can see that if we drop the diameter from 130 centimeters to 120 centimeters, we can get rid of the height warning issue, but we've added 2 others. We now have a pressure drop that's above our recommendations, and we actually have a linear velocity that's above our recommendations. So
Garth, can you comment on the recommendations are?
With the pressure drop.
No, me first. Me first.
Yeah.
Sorry about it. Go ahead.
This is a good cut-in for a question that came in from the audience on the drop for a mixed bed. So we just want to highlight that. It did come in, and we have a limit built into Wave here that would prompt it at 1 bar.
I think we were asking the same question. So.
Yeah. No, I know. That's.
Anyways,
while we've broken in, can we also just comment? Someone asked about how their end users usually ask for 168 hours of throughput, and if we could have run it that way. And of course, we started this design with spatial velocity, but if we were targeting a specific run length, we could have put that as the input on the input screen. Yep.
Yes, we could have specified either. The velocity usually is what I tend to use for mixed beds. But yes, you could specify run length. In this particular design, we're actually getting just under 95 hours. So the flow rate's not too far off from what you would need, or the BVs per hour is not that far off. The other question is the pressure drop. Yes, there is a limit built in for this kind of mixed bed with these resins. The limit tends to be about 1 bar pressure drop. And so in this design, by dropping 10 centimeters off the diameter, we can no longer meet the pressure drop limit, and we also start hitting a linear velocity limit. So making the bed narrower and taller is not going to help us to clear all the warnings we saw in the previous test. So what we're going to have to do is probably slow down the flow rate a little. So we tried 50. We can either do operating cycles, or we can reduce this, say, to 40 BVs an hour. Run the report. And we will go to the polish report, and I'm just going to jump to the bottom. I have the exact same warning. What has happened, if we scroll up just a little, the vessel diameter went up from 130 to 140. I have more resin, and the system decided that I wanted a slightly larger resin vessel diameter. However, if we take a careful look, we can see that the pressure drop here is 0.81, so I actually have a decent amount of range between where I am and the limit of 1. And as before, we were, we were below 40. Now we're, about 42. So we're actually getting pretty close to the height limit. So by trial and error, you could decide, well, what happens if I put in, say, a 135? So if you can actually specify and get a custom vessel diameter, you can play with that a little. And that would essentially clear the warnings. At this point, the limit is 45, or right at it, so it's within the rounding to 1 decimal place of hitting it correctly. So we now have a design that met our requirements and has no warnings of consequence.
Okay.
Okay.
So do we want to look at a scenario where the RO performance changes?
Yes. So, yes, and there's something to be careful of when you are talking about changing the RO performance. When you do that, we are set up to design a new plant. So that means if I change what's in front of it, I'm likely to get a brand new plant design behind it. Which, in reality, your ion exchange plants, you don't keep rebuilding new ones. You're going to have a fixed design. So having decided that this is the optimum design, we want to lock it down. And then we'll start playing with the RO and seeing how that affects the ion exchange behind it. So what you can do is, once you have a new plant design that you're happy with, and you've run it, and you actually see final parameter adjustments down here, if you click on Evaluate and sort of ignore the first pop-up warning, you get a second one. Do you want to copy the design or start a new design? I'm going to say copy. And what that does is creates a new case and then copies over what had been a final parameter adjustment for a new design. And now we're doing an Evaluate. And all those numbers got copied in. So this is the same design we were looking at as new, but we've now fixed it. So we can't change it. Well, you could manually change it, but the system won't automatically change it. And looking at the initialization page, you can't specify run length or SV anymore. Everything's locked down. But we're now going to look at what the runtime is. So now as we change the conditions that we're running under and the RO performance changes, we will watch the mixed bed performance change. So for example, let's go look at our summary report again.
just to refresh. And Garth,
Okay.
you're talking about changing some of the conditions of this RO design, which have also been frozen. But presumably, if someone had a plant, they could not just change conditions like water temperature, but they could take this fixed design and change RO elements to see how that might impact their mixed bed as well, right?
Correct. So at this point, Matt, you are correct. We have essentially locked down the ion exchange system, and we can now make numerous changes to see what happens. After everything is said and done, we have a initial run length of 118 hours using our design temperature of 12 degrees C. So you could say, okay, what happens if we change the design temperature? I think they said they had a minimum temperature of 5 degrees. Okay, as we go from 12 to 5, things are going to change. The water is going to get more viscous. That'll affect pressure drop. The RO performance will change. So if we take a quick look, we just refresh the report. We haven't changed anything except the running temperature. So we went from 118-hour run length to 160-hour run length just by changing the temperature. And that's due to the temperature dependence of the ion exchange performance and the temperature dependence of the RO performance. But you can see it had a dramatic impact on run length. Checking to see if everything else looks fine. You can see we now added, we still have this little 45 rounding limit, but you can see we now have a pressure drop warning. I guess that's not unexpected. We are very close to the pressure drop limit before, and we drop the temperature, increase the viscosity of water, increases the pressure drop. So in this particular design, at the design conditions, your pressure drop is fine, but if you run towards the low end of the limit, you might have to worry about pressure drop exceeding the recommendations at low temperatures.
And there is some just if there's an awareness of that over the course of the temperature range of operation. This one bar is set as a warning level, but it's not necessarily a hard and fast. And for even different applications, we might have different limits, such as for condensate polishing, or just being aware that we're trying to give you the heads up that you're creeping up in pressure drop for a new design, but you may, with awareness, make some decisions in your design and how you want to operate.
Correct. And you might decide to go to a different resin that has a higher limit, for example. There are multiple ways you can address that. If we look at what would happen at a very warm day, we'll specify a temperature and we'll pick 25 degrees. So we went from 12 degrees to 25 degrees. And we look at what happened, and you can see our run length went flying down. So now it's about 66 hours. Yes.
Garth, I think there's one more feature that we want to show, and we should probably move to it because we're getting to that point where we're going to need to wrap up pretty soon.
Sure. Okay. So just finishing off, as you see, we raised the temperature and the pressure drop came way down. So the feature Matt was talking about is we're introducing in the next version of Wave that everyone can download. Is this
sneak peek here?
Yep.
Yes. Sneak preview. It's this feature called the water quality adjustment icon. And this allows you to manually change the water quality between icons. So we will take a look at it. And you have several things you can do. And essentially, this would allow you to manipulate just about every concentration coming off one icon before it goes into the next. Right now, we're multiplying everything by a factor of 1. if you wanted to say, put in a safety margin of 1.25, this would multiply all your concentrations by a factor of 1.25. So it would raise all the concentrations by 25%. You could see the impact that would have on your run length.
This is a nice feature.
Yes. Alternatively, you could decide that you want to manipulate specific concentrations. So for example, silica after our one pass RO, we could say, let's make sure we design for no less than 1 ppm or whatever number you think appropriate. So what would happen is we have a minimum concentration. We set it at 1. Wave will run the design. If the RO silica level is above 1, that's the number that would be used for the mix bed. If it goes below 1, it will use 1 to design the mix bed. And you can do this for any of the species. Normally, you would do it for the performance limiting species, for example, silica on the anion resin. And then you could, having specified that, you just rerun the report. And we were at a high temperature, which I believe had a high silica level. Yeah, so it had no impact on the design because the actual silica coming off the RO unit in this case was 1.39. But if we go back to the minimum temperature and rerun it, and go to the polish report, you'll see that it fixed the silica at 1 as you had specified. So this new feature, the WQA water quality adjustment, will allow you to tweak the design based on your experience if you want to put in safety margins or things. And I think that covers the 2 main examples we had. Yep. So now we can take questions.
Great.
Garth, just as you're getting to questions, do you mind just clicking on the detailed report to show everyone where that
sure,
how they find the impact of that?
Sure. Okay. Yep, I forgot to mention that, so thank you for reminding me. If you have a water quality adjustment turned on, when you go to the detailed report, let's blow this up a little to make it easier to see. If you go all the way to the end, you'll actually have a page, a report that you use the water quality adjustment factor, and it'll give you the essentially the concentration going in and the concentration coming out, and you will see that everything's the same except for silica. I raised the silica from 0.39 to 1. And depending on the change, you don't lose track in your report what you did. And one thing to make note is it will recharge balance the water after you do that. So if you were to change, for example, sodium or something by that much, and not everything else, it would swing the pH a lot. So you got to be careful when using the water quality if you start moving charged species up or down too much without something to balance it, because you'll swing the pH around.
Okay. And you're already starting to get some positive feedback on that. Go ahead, Donna.
Would now be a good time to ask. There's a question about reports. Is it possible to view multiple summaries at one time? For example, if you change the water temperature for 3 scenarios and view the summaries side by side.
Okay. So at the moment, you cannot run multiple projections and see multiple reports at the same time in the wave screen. If we were to take this specific design and copy it and then run it at each of the temperatures, so if I go back to home, for example, and add a case, and then make this, we're now in case 3, and I change the temperature from, we'll run it at, 15. There's an option, I changed the temperature. You need to adjust the pH to rebalance. You run the report, and then you would have, that's an interesting one. We'll have to figure out what happened there. Normally you would have, let's go back to.
Normally it'll print out with multiple.
Yeah, you can create multiple cases.
In the
there's an option. Yeah, there's an option which I was trying to. Oh, now everything's failing to converge. Okay.
Sorry, it's okay because we're getting prompted from our production team that it's about time to wrap up. So maybe if you want to stop sharing your screen, we can just do a live goodbye. And as we're transitioning, one question came in about the WQA. Can you add multiple WQA M&Ms after different unit operations? Is that something I don't know the answer to?
Yes, you can put a WQA between any pair of icons.
Okay.
So if you had, a UF-RO mixed bed, you could put in 2 WQAs, one after the UF and one after the RO.
Mm-hmm. And I wanted to just address the question on resins, why use this resin versus that resin. And like when you're changing to a condensate polishing application feature, is that going to be a different selection of resins or the same?
That would be a different set. We have a set of resins that are recommended for working mixed beds. We have a different set of resins for polishing mixed beds, and we have a third set of resins for condensate polishing. So the 3 different major areas where you would use a mixed bed each would have a different list of resins.
Mm-hmm.
All right. Anything else you want to say? Otherwise, I think now is a good time for us to say goodbye.
I have nothing else. Just thank you, everyone, for joining our WAVE webinar today. I hope you learned something useful and interesting, and to make WAVE more useful for you. And be sure to send us any questions you have so that we can answer them. And if you have any issues with WAVE, please let us know so we can get them fixed. The best place to send them is our WAVE mailbox, which is ffewave@dupont.com. Okay, Donna, Matt?
Thanks.
Yep, thanks for joining.
Yep. Thank you, everyone.
Thank you, everyone.
Bye.
Have a good day.
Bye-bye.
Stay safe.
Take care.